Greetings, YouTube. Beautiful mind here. And this serves as the last lecture for chapter 1, right? So we've been making our way through chapter 1 on differentiation. And so today we'll be looking at section 1.8, higher order derivatives, and a couple of objectives that we have. We like to find derivatives of higher order, and given a formula for distance, find velocity and acceleration. Okay. So higher order derivatives, let's consider the function given by this, right? We have y equals this, x to the 5th minus 3x to the 4th plus x, right? Is derivative, so if we take the derivative, right? Remember the 5 comes down and we subtract 1, we get this term. The 4 comes down, 4 times 3 is negative 12, and we subtract 1, that's where the 3 comes from. The 1 comes down, and then 1 minus 1 is 0, x to the power of 0 is 1, so then this, the derivative of this is just 1, right? So the derivative function f prime can also be differentiated, right? So we took the derivative. Now we want to consider, what if we take the derivative again? We can think of the derivative f prime as the rate of change of the slope of the tangent lines of f, right? It can also be regarded at the rate at which f prime is changing, okay? Derivatives continue. So we use a notation f double prime for prime, right? That is f double prime is d by dx of f prime, right? We're basically just taking the derivative of the derivative. We call f double prime the second derivative of f for y equals this, right? The second derivative is given by, so where is it? Well, anyway, we just take the derivative of the derivative and the solution that we get is here, okay? So for higher order derivatives, we use a notation like this to express the nth derivative of f. Continuing in this manner, we have the third derivative of f, so we can take the derivative of the second derivative. We have the fourth derivative and the fifth derivative, right? Okay, in this case, we can go at least to the fifth derivative. See it, fifth derivative is here. So then the sixth derivative, if we take the derivative of a constant, that's where the 0 comes from. And so the nth derivative of this function is going to be 0 for any derivative greater than or equal to 6, right? For this one, once we hit the sixth derivative, it stays 0 from that point on. Okay. So Leibniz notation for the second derivative of a function, so the dy by dx, is the second derivative of y with respect to x. It looks like this, right? Or d by dx of dy by dx, right? Again, this is read the second derivative of y with respect to x. The 2's in this notation are not exponents, right? So they're not exponents. We're not squaring anything. That just means take the derivative twice in this case. Y is given by this, then the derivative of y with respect to x, or in other words, our dy by dx is this, right? The second derivative, so basically the derivative of this, the 4 comes down, 3 times 12 is negative 36, derivative of a constant is 0, we get this. The third derivative is here, the fourth derivative is here, and the fifth derivative is here. Once we go to the sixth derivative, it's 0 from that point on, right? Well, we have this y, we're asked to find the second derivative of y with respect to x, okay? I usually like to start with a copy of the original, like this, right? So then dy by dx, we could use low d high. I'm going to consider this in this form, x to the minus 1. That's just easier for me. So now when I take the derivative of x to the minus 1, the exponent comes down, and then we subtract 1 and we get x to the negative 2. But then this is going to be negative 1 over x squared. If we use the quotient rule where we say low d high minus high d low over low low, we would get this result, all right? Okay, but we want the second derivative, so we want d by dx of this one. So then we're going to have the second derivative of y with respect to x. Okay. Use this part here because it's just easier for me to see. The negative 2 comes down, so double negative becomes positive. So becomes positive. Nope, that's not a 2. And then we subtract 1 and we get to the negative 3, and this is the same as 2 over x cubed, right? I wish there was a way I can set the default thickness of these. And I make my way through the settings or whatever. And you see it here, 2 over x cubed, okay? So for this example, find y prime and y double prime. So find the first and second derivative, all right? Okay. Initially, we have y equals, we have x squared plus 10x all to the power of 20, right? So we have to use the extended or like the chain rule, right? The chain rule. So for y prime, the chain rule goes is going to be the derivative of the outside function times the derivative of the inside function. So that means the 20 comes down. We just rewrite the inside function. 20 minus 1 is 19, and then we're going to say times. The derivative of the inside function is going to be 2x plus 10, all right? So that's y prime. Let's see, can we simplify any? No, let's just leave it like this, right? The y double prime, it looks like we have to use like product rule, chain rule, several rules in one go, right? So product rule is the first, which is this guy. Derivative of the second, so that's going to be what, times 2? And first, so that means the 19 comes down, what is that, 380? So then we're going to get 380 now. Then we're going to have another x squared plus 10x. Now it's to the power of 18, and then times the inside function. The derivative of the inside function is going to be 2x plus 10. Okay. On one line. Just a little. Let me see. Now we have some like terms. I'm not going to expand this all the way out, but we can like combine some of the stuff. Like for instance, we can factor out that x squared plus 10x. They both have at least 18 of those. So let's go ahead and capture that. So then y double prime, they both have this x squared plus 10x, and they both have at least 18 of those, right? If we're going to have 20, there's still one of those left. So x squared plus 10x. 20, I'm going to go ahead and change that to 40. That one out over the x. Identify that. This we factor all the way out. That 2x plus 10 squared left over. Here. Plus 10 squared. And I think that accounts for everything. More time. 380. And I think I need one more set of parentheses. 1, 2, let me see. Open, open, close, open. You can go a little further. Like we can expand and simplify that second part and combine a lot of like terms. I'm tempted to do it. I'm gonna look and see. Let's go ahead and do it because it's not, I think the hardest part, I think we got past the hardest part. Y double prime, x squared plus 10x to the power of 18. Now, if we expand and combine like terms, we'll have a 40x squared, 400x, 380 times, it's going to be what, 4x squared x plus 100, okay? Here, x squared plus 10x to the power of 18. Now, they probably stopped way sooner than we did. X squared, 4 times 380, 4 times 3 is what, 1200? Plus 320. So 1560 if we combine those x's. What's 380 times 40?
40 is 15,200.
1500. Greatest common factors we can factor out of this, but I'm just going to kind of go with it for now. And then add 2 zeros on the back of that. 380 with 2 zeros on back. Okay. Now again, we could go through this and factor out the greatest common factor of those constants, of those coefficients. But I'm just going to kind of stop here and look and see where did the note stop. Okay. Yeah. So they did factor out that 40. Let me see if I factor out that 40. Right now, y double prime. Now, if I factor out 40, x squared plus 10x to the power of 18, 1560 divided by 40.
1,560 divided by 40 is 39.
Okay, 39x squared. I think that was 390. 38,000 divided by 40.
38,000 divided by 40 is 950.
Kind of neaten this up a little bit, like this, like this. Give me just a moment. Like, I don't want to be like a lot of them are going to be like that, and I don't really want to give you a lot of stuff like that. Like if I come across those, because you don't have to. It's not really about being that meticulous or anything like that. Um, you know. So, oh, I meant to put this in a box. Here and here. Okay. So the second derivative, I mean, they essentially did the same thing we did. They got the same result, 39, 390, and 950. There's the 40. I did borrow the 40 because I just didn't feel like looking for that number. Um, we can find it and just, okay. So the quick checks I usually leave as an exercise. So I'm going to leave that for you. Just give it a go. And if you want to talk about any of them, we can. And I think here's a solution for those. Right? So we kind of, and so the concept behind higher order derivatives is simple. It's just basically derivatives of derivatives, right? You just kind of keep taking that derivative, but you can see how quickly it can kind of it can get nasty kind of quick, right? But the main thing is that you get the concept, right? And then just practice, and you'll get better. So then we have this definition. It says the velocity of an object that is s of t units from a starting point at time t is given by this, right? So if s is your position function based on time, then the velocity is going to be the derivative of the position function, right? Again, the limit definition of derivative is going to be limit as h tends to 0 of the position s of t plus h. Again, h is just some small change on the x-axis or the t-axis minus s of t over h, right? This is just a limit definition of derivative like we did before, like how when we first introduced derivative. Acceleration is going to be the derivative of the velocity function, which is going to be essentially the second derivative of the position function. So you have some function that tells you the location of some object based on time. When you take the derivative of that, that gives you velocity. And then when you take the derivative of the velocity function, that gives you the acceleration function. Okay. Well, for this position function, find the velocity function and acceleration function where s is the distance from the starting point in miles and t is the hours. Then find the distance, velocity, and acceleration when the time is 4. Okay. So our position function here, function, our v of t is going to be s prime of t. And that becomes 20t, right? And then the acceleration function is going to be v prime, which is 20. Now let's see. In hours, right? So velocity, those units are miles per hour. We can just put mph or miles per hour. And then this is going to be miles per hour squared, all right? So acceleration is in the units of like, basically in this one, it's like miles per hour squared, okay? Velocity when t is 4. So then s of 4 is 10 times 4 squared, 16, so 160. They should have traveled 160 miles. Speed for 4 hours of speed should be 4 miles per hour. Acceleration at 4 hours. I think we have a constant acceleration, so it's just going to stay 20 squared. No box it anymore. Hour, and then the acceleration is 20 miles per hour squared. Let me move this. 4 hours, it should have gone 160 miles. Of 80 miles per hour. Constant acceleration of 20 miles per hour squared. Okay. T acceleration was 20, 160, 80, and 20 miles per hour squared. As an exercise for you, okay? Again, just give it a go and just contact me if you'd like to talk about it or if you need me to work through it. And then, so three is the derivative of the first derivative of a function. In symbols, f double prime is the same as d by dx of f prime. In other words, it's a derivative of the derivative. The second derivative describes the rate of change of the rate of change. In other words, it describes the rate of change of the first derivative, right? The second derivative is acceleration. If s of t represents the distance as a function of time of a moving object, then v of t is s prime describes the speed or velocity of the object. Any change in the speed of the object is acceleration, which is going to be v prime of t, which is the same as s double prime of t. The nth derivative of a function is the nth derivative of f, or the nth derivative of a function with respect to x. I think that wasn't too terribly bad. It could have gone much worse. Okay, hopefully this is okay. So that kind of wraps up differentiation. And so next time on Dragon Ball Z, we'll be looking at next time on Dragon Ball Z. We'll be moving into chapter 2. So we want to kind of go ahead and start getting ready, getting our minds set up for exam 1. That's going to occur, I think I scheduled it for week 6. We have 2 in-class or 2 exams and then a final, right? Exam 1 is over chapters 1 and 2. Exam 2 is over chapters 3 and 4. And then the final is basically beginning to end. I think I've scheduled all assignments, like again, all of our homework for the entire semester are posted and available. All of our quizzes for the entire semester are posted and available. The only thing left are going to be our 2 exams and final, which will become available during the weeks as listed in the syllabus. So basically, exam 1 is week 6. Exam 2 is week, I think it's like 13. And then the final is the final exam week, right? All right. All right, guys, good luck. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.